Hi, today we're going to talk about a measure of how strong or weak an acid is. And this is called by a couple of different names. Some books call it percent ionization, some call it percent dissociation. I'm mostly going to call it percent ionization in this video, because even though this video is only talking about acids, you can also use it for bases, and bases don't really dissociate. They gain things, they don't lose things, but they do become charged, and so percent ionization works a little better for that. Basically, there are two ways to think about how strong a weak acid or base is. And now I know it sounds a little weird to ask how strong is this weak acid or this weak base, but some weak acids dissociate more than others. And so the ones that dissociate more are stronger. We've already talked about the Ka value, and you know that the larger the Ka value, the more products you get in your dissociation reaction, and therefore the more H plus you have. And so if the strength of an acid is linked to the H plus concentration, the larger the Ka, the stronger the acid. The other way to do it is, as I said before, the percentage of dissociation or ionization. Now we are talking about percentage here. That is the way that people normally talk about this in Gen Chem. However, in some branches of chemistry, we use a fraction of dissociation or ionization, and that's very much related. So the equation for percent ionization or percent dissociation is going to be the number of moles ionized per liter divided by the number of moles available per liter times 100%. So I said earlier that some people use the fraction of dissociation. That would just leave off times 100%, and it would be the same equation overall. All right, let's look at this equation. There's a bunch of words in there that might sound like gobbledygook. So the moles ionized per liter is basically the number of moles that become the charged form of your acid or base. So that would either be your conjugate base of your acid or the conjugate acid of your base, A minus or BH plus. We also have the number of moles available per liter in the denominator of our fraction, and that's basically the total number of moles that could ionize. And there's two ways to think about this. The first is to say, how much HA and A minus do I have in my acid solution? Because HA can turn into A minus or vice versa. So that's how many moles of acid there are, right? If you're dealing with the base, it'll be the base and its conjugate acid. So add those concentrations up. The other way you can think about it is they have a problem where they basically say you start out with this many moles or with this concentration of the acid. That's the number of moles available. And I am saying moles here, but it could also be concentrations. That ends up working out to the same thing, because both the ionized and the unionized acid or base are present in the same solution with the same volume. So quick application of that. Here we have benzoic acid, which is a solid acid, being dissolved in water to make a 0.1 molar solution. And then you go through and you find the concentration of benzoate, the conjugate base of benzoic acid, and you find that's 2.47 times 10 to the minus third molar. So we go to our equation, and we're looking for the ionized number of moles or concentration for the numerator of our fraction, and that would be our A minus concentration. And we're looking for the total moles of HA that were added to the solution in the beginning for the denominator. So there's our A minus concentration, and there's our HA concentration, and our percent ionization then is going to be 2.47 times 10 to the minus third divided by 0.1 times 100%, and that will give us 2.47%. As you can see, with a fairly weak acid, there are very few molecules that actually lose their protons. It's just a very, very small fraction. So of course, because it tells us about the strength of an acid or base, is linked to Ka, or when we get around to doing bases, you'll see it also is linked to Kb. And to figure out what the Ka or Kb is from the percent ionization, we're going to start, as we always do, with an ice table. And we'll fill in the known concentrations. Then we can calculate the change in whatever our ionized species is, either the conjugate base of our acid or the conjugate acid of our base. And then we use stoichiometry to calculate the other concentration changes. And then, as always, we calculate the equilibrium concentrations and plug those into the Ka or Kb expression. So here's a problem where we know the ionization of hydrofluoric acid, HF, and we know the concentration of that hydrofluoric acid solution, and we're trying to find the Ka. So we start, as we always do, with an ice table, and we plug in our known concentrations. Again, we're assuming that our initial concentration is all in the undissociated form, the protonated form of the acid, and everything else is 0. So now we're going to calculate the change in this case, F minus concentration, using our percent ionization. Basically, we know that 29.6% of our initial concentration ends up in the ionized form, so we're going to multiply those, and we get that 0.0189 molar exists as the ionized form of our acid. So let's plug that into our ice table, and now we're going to calculate the other concentration changes. And as always, we're going to have the same change with the H plus concentration and the negative change in our HF concentration. Now we can calculate our equilibrium concentrations. That gives us 0.0451 for HF, 0.0189 for both F minus and H plus. And now we can take those concentrations and we can plug them into the Ka expression, which, remember, looks like this. So we plug those concentrations in and run it through our calculator, and we get 7.92 times 10 to the minus third. Now, we can also go the other direction. We can take our Ka value and use it to calculate percent ionization. In this case, we're going to calculate both the pH, which we've done before, and the percent ionization, and you will see that they follow similar tracks. So we're going to start with our ice table, plugging in the initial concentrations, and then we set the change in H plus to X, as we did when we were calculating pH. Calculate the other concentration changes using our stoichiometric ratios, and calculate the equilibrium concentrations, substitute those equilibrium concentrations into our Ka, solve for X somehow or another, hopefully the easy way, use the value of X to calculate the pH, and also then use the ice table values to calculate our percent ionization. So let's go through and do those 7 steps. Here is a problem where we're looking at a solution of 2-methylaniline, and we're given the Ka. So I made an ice table. You'll notice that I didn't put in methylaniline. I've just put HA because I may know what methylaniline is, but I know that you don't. We see that it has a Ka, so we know it's a weak acid, so it's just going to be HA, and then A minus for the conjugate base. We set our H plus concentration equal to plus X, and then we calculate the other concentration changes. A minus concentration will also be plus X. HA concentration will be minus X. And so we calculate our equilibrium concentrations, and we get X, 0.43 minus X, and X. All right, let's substitute those equilibrium concentrations into the Ka value. But before we do that, I'm going to go for that shortcut. And I'm going to say that 0.43 minus X is approximately equal to 0.43. So let's go ahead and plug those into our Ka value. And remember that our Ka we've been given is 3.57 times 10 to the minus fifth. And now we can solve for X. So X squared is going to be 0.43 times 3.57 times 10 to the minus fifth. X will be the square root of 1.53 times 10 to the minus sixth. and then our x value will be 3.9 times 10 to the minus third. When you plug those into the equilibrium concentrations, you see that our 0.43 minus x rounds to 0.43, and that's great. That tells us that our shortcut worked and is a valid shortcut. So let's use x to calculate pH. pH is negative log of H plus, which is negative log of 0.0039, which is 2.41. So now let's use the values in our ice table to calculate percent ionization. Remember that the percent ionization is equal to the moles ionized per liter, which in this case is our A- concentration at equilibrium, divided by the moles available per liter, which is the initial HA concentration, times 100%. So that's 0.0039 divided by 0.43 times 100%, which is 0.91%. So this obviously doesn't dissociate very much, less than 1%. Percent ionization, again, is another way to help us understand how strong or how weak an acid, or also a base, is. I hope this is helpful, and I will talk to you again soon.